Hey, Professor Tack.
Yep.
Just a quick question. So we all got the email with our tests the other day. Were those supposed to be like just our versions of the test?
Yes.
Okay, cool.
Did you get somebody else's?
No, no, I did. I didn't know if it was supposed to like be the generated answer key.
Oh, yeah, I can actually distribute the generated keys as well. Except I'm using those for grading right now. Um, and the grading is taking a little bit longer because when people report the properties of a relation, I have to, if it is not correct, in their submission, I would actually indicate why it is not correct. Like if something is supposed to be true and the answer says it's false, I have to kind of explain why that is the case. So it's taking a little bit
Yeah.
longer too, because it takes me about 15 minutes to 20 depending on the on the answers to grade one single question to grade one complete one. So it's taking me a little bit longer this time, uh, even though I have all the keys with me.
Oh, that's no problem. If you're willing, that way we could get kind of like a rough estimate ourselves. If you
hmm
were willing to pass out the answer keys test,
Yeah, I can do
obviously it
that.
wouldn't be the official.
Yeah, no, not a problem. I can pass the answer keys. When I'm done with today's lecture, I'll modify the script to also distribute the key files. Because I for each question for each exam document, I also have a key document, which is really just a plain text file, but it's automatically generated. So okay,
Okay, perfect.
yeah, I'll
Yeah,
keep that in
thanks.
mind. Okay, we got about a minute or so to go, and I'm going to look up a few things that is off the screen so you can't see this part. So how was the program? How was the homework assignment?
Well, I did it 2 times, and I'm about to do it a third because each time I still stored it on the stack.
Ah, yep. So I think this one is actually a pretty good example of a recursive, the application of a recursive subroutine. Uh, the permutation generator is actually easier compared to the combination generator, because with the combination generator you cannot ordering is not important. So there's a cheap and easy way to do it, and then there's also a more expensive way but seemingly more proper way to do it. So there are several ways to get things done for the omega generator. um, I'm just checking here to see how many people have turned it in. Okay.
It was tricky though, for sure. Like if you didn't realize to use recursion, which obviously you talked about later, but before that, I'm sure a few people tried loops.
Well, the definition is already recursive, so I thought that was a suggestion already, just because of the definition itself being recursive.
Could you
Uh,
have done it with for loops out of curiosity?
Well,
Or would that
everything, well, theoretically speaking, everything that you can do with recursion, you can do it with a for loop. But in this
yeah.
case, if you were to do it with a for loop or nested for loop, you would have to use a stack to maintain the trials,
Oh,
to maintain
okay, yeah.
information of the trials. So so yes, you can do it without using recursion, but then you have to basically manually manage a quote unquote stack that keeps track of all the trials. So when you're done with all the trials, you have to kind of back up the stack. You have to pop, and then you have to push again. So instead of using recursion to do all the pushing and popping, you would have to then rely on your own logic to do all the pushing and popping, which I think is less intuitive. It's more intuitive just to use the recursive approach to do it.
I
All
think
right.
so too.
Yeah, go ahead.
Oh no, I was just agreeing.
Oh, okay. All right.
Would you
So,
have picked what? I'm just want your opinion on this. What language would you have picked to do this if you wanted to do it the most effective and efficient way? Because I
all
know that
right.
there's different languages for different.
So, in terms of a language that has a lot of built-in features to help you with this homework assignment. The best one, or the one that I know the most about, that I think is going to be pretty easy, would be JavaScript, or any type of scripting
Literally.
language. Would not be a bad choice. Just because they can manipulate strings pretty easily without having to call like string copy or string cat or stuff like that, and you don't need to, and you won't run into problems like where's my null terminator, because in C and C++, especially in regular C, if you don't terminate a string, which is really just an array of characters, or if you do not allocate enough characters, then you have a problem, because the program will basically doesn't know when to terminate, or if it runs over the boundary of a string, it doesn't know it, and then you start to corrupt other things on the stack, and bad things will happen. So a scripting language can basically save you from all of those things, all of those problems. So for that matter, Java is also not a bad programming language for this. Okay, so it is time. Okay, it's 12:02. So if you guys want to, I can kind of show you, how to approach this problem. Or if you guys say, well, I've done it already, I don't need to look at another solution, then we can just, kind of move forward to talk about graphs. So it's up to you guys. Which way do you guys want to go?
I would like a walkthrough, please.
Yeah, me
Walkthrough?
too.
Okay, all right. All right.
Thanks.
So I'm gonna go through a walkthrough of how one way of doing this. So by no means am I saying this is the only way to do it, but this is one way to do it. So I'm gonna go start with I think I got the yep. So I already got a portion of it written. Okay, let me use the other one. I got two vims here. Okay, this one is slightly better because the syntax highlighting is a little bit more clear. All right, so this is what I gave you guys last time, which is a recursive subroutine to print a random string, okay, which is kind of a hint of what you guys can do, with your permutation program, but it doesn't go through all of those things that you have to go through. So we're gonna change this, if argc is greater than or equal to 3, because this time we also need the two parameters. And I'm looking into the homework description off your screen, but it's on mine. argv1 is a base 10 number that is the number of trials. Okay, so I just need to make sure that I use the right names for the variables. And then the next one is the number of choices for the first trial. So that's atoi argv2. And I'm going to assume that both of these are actually numbers, and I'm not going to go for any type of checking to make sure that they are in fact numbers and they're not negative and stuff like that. All right, so I can even keep this one here. I can keep the malloc. Basically, I just need to know how many bytes I need to allocate for the string that I am going to print eventually for each experiment outcome. Okay. So this is going to be, length is gone, so the name of length is now num trials. And I still need +1 because I need one more byte just for the terminator. So regarding this, there are several ways to do it. It depends on, do you want to push some extra stuff on the stack so that how to trace your way back to find the beginning of the string. Okay, so both way works, and both way requires that one extra byte to mark the end. So the question is the beginning the end of the string, or is the actual end of the string the end of the string? So it sounds really kind of awkward, because the first question asked, do you want the beginning of the string to be the end? Because when you print a string, nobody says you have to print from bracket 0 all the way to up to ending, excluding the null terminator. You can always print the backwards too. So you can start from the last character and then you move backwards until you find the null terminator. So I'm going to use that approach in this case. And then we'll start to write the subroutine. So as I write the subroutine, I'm going to change this call here. The call on line 31 is going to change depending on how I write the permutation generator subroutine. All right, so here we have, I'll just call this omega. it requires a few things. Okay, for sure it requires the number of trials. Okay, so number of trials is basically including this invocation. How many trials are needed for the sub experiment from the perspective of this invocation? And then the other thing it would need is a const char. Not const char, it's a char pointer. It's not const because we're going to change this location. Okay, so we'll call this my choice. Okay, let's see, what else do we need? Well, interestingly, I think we don't need anything else. Yep, okay, so, alright. Alright, so I'm not even going to implement the notion of a set because, for this particular program, it doesn't really help to have, set primitives like unions, intersections, is this an element of, and stuff like that, because the operations that we need to do is fairly simple, so we don't really need to have the concept of a set. Even though, for those of you who want to do it that way, it's fine. Okay. So the other thing I want to do in main is basically to say str bracket 0 is a null character. In other words, I am treating the first character of the entire array critical as the end. Okay, so everything after that is going to be one more than that. So when I call omega, I'm going to call omega with num trials, which is the same as what I read from the command line. But when it comes to the string, I'm going to pass string plus 1 because string, the first character of string already has a null terminator. So the first invocation of omega will basically put its choice into the second character of the array. Okay. So from this perspective, from the omega's perspective, I mentioned this a little bit in the Friday special, the TGIF special on Friday. Of this kind of programming is because we have object-oriented programming, right? So this one is more of a invocation-oriented programming. We look at the logic from the perspective of what does this invocation has to do. Okay, so this is one way to kind of make recursion easier to understand, is only to look at this from the perspective of one single invocation, assuming the function is already done correctly. Okay, so you can probably connect this line of thinking with proof by induction, where we have the induction assumption, which basically says, let's just assume the theorem is already true for all the cases from 0 up to k, and now we're only using that to help prove the case of k plus 1. Okay, it's kind of the same thing. So what we need to do is to find out, okay, when can we stop? Okay, when num trials is 0, this is when we can stop. Okay, even when it's 1, we still got some stuff to do. Okay, so I just automatically put in the framework of a conditional statement, and we'll go ahead and handle the easy case first. Okay, when it says, okay, there are no more trials left. Okay, so when there are no more trials left, then it's time to print out the permutation that is already stored in the string. So my choice is supposed to be the place where this invocation is going to store its choice, but since this particular invocation has nothing to do because it has got no trials left, so what we need to do is to go backwards and print the string in a backward manner. So what that's going to look like is while, okay, I'm just trying to see if I can use pre-decrement. Yeah, I can use pre-decrement. Okay, so I can do a while star, okay, asterisk minus my choice. And so when I get into the loop, that means my choice is not pointing to a null at this point. So that means I can use putchar to put this on the screen. So putchar is one of the really primitive function calls in C or C++. Okay, let me just kind of, oh, okay, that's not what I want to do. Let me try that one more time. Putchar, okay. Okay, so the putchar is right here. All it does is to print the character corresponding to the integer c. So you just give it a char, okay? Even though it takes an int, all it does is to use the least significant byte and print that out as a character. That's put char, which is no different from just see out a single character. Okay. So I'm going to use put char. Oh, this is the wrong subroutine. Okay, never mind. Let's go back to the one that we're supposed to be doing right here. So we use put char, and we're going to print whatever my choice is pointing to at that point. Now, because I'm using a pre-decrement over here, so by the time we get to put char, it's not going to be my choice as a parameter. It is going to be the one right before it, or starting with that one. And then this loop will keep going and going until my choice is pointing to a null character, which is the very first null character that main puts into the entire array. Let me just go back to here to let you know which one. So on line 45, this is where we put in a null character at the very beginning of string, and by the time we get to over here, we just have to go backwards until we find that null character at the very beginning, and then after that there's nothing else to do except to put char, and then this time we need the ASCII code of the line feed characters, which is just 10 in decimal. Okay, so that handles the end of the recursion. So what if num trials is non-zero? Okay, I need to look at Discord again, make sure there are no questions. Okay, there are no questions right now. So this part here, okay, between line 33, the braces of line 33 and line 35, is I need to handle the case when, okay, we have at least one trial, which means for this, from this invocation's perspective, it has got stuff to do. Okay. So what it needs to do is to go through every single possible choice and ask, which one can I use? Okay, so that means I forgot one parameter to omega is the number of choices. Okay, so I need to pass num choices, because otherwise I would not know when to stop. Okay, can I only use A, B, C, D, or can I use A to Z, or should I use A to O, or should I use A to T? That information needs to be passed into the subroutine. So I will add one more thing here, which is int num choices. Okay, so when we get to line 34, it is all about my choice. Okay, which is this pointer here, is what can I put into that location. Okay, the only restriction is I can use any one of the choices. So if num choices is 26, for instance, then I can potentially use lowercase a to lowercase z, but I cannot reuse something that had already been used in the prior trial. Okay, so that becomes the challenge. So the first one is really just to look at the choices that I do have, okay, and then we'll figure out, can we still use it? Okay, is it already used by a previous choice? So there are several ways to express this. There's no need to use a temporary variable for this purpose. We can just go ahead and start with lowercase a, and then we say, my choice is less than lowercase a plus I suppose we still need a local variable to mark the end. There. Okay. I'm just kind of grunting here because I'm trying to figure out a way so that I do not need to use any additional local variables, and I can do it this way. Probably need some typecasting so that the compiler doesn't complain about it. So when I'm done with this line, I will explain what this outer loop is going to do. So the outer loop, okay, if you just look at the for line on line 34, basically it says, my choice is going to start with lowercase a, and as long as the difference between what my choice is pointing to and lowercase a is less than num choices, I'm still good. I should still stay in the loop. And for each iteration, I also want to post increment whatever my choice is pointing to. So note that I use parentheses around star my choice, which means I'm not incrementing the pointer itself. I'm incrementing what the pointer is pointing to. Okay, so basically what my choice is pointing to, that one single character will start with lowercase a, then lowercase b, lowercase c, and so on until I run up to the maximum, which depends on num choices. If num choices is 26, I will stop at lowercase z. If num choices is 4, I'm going to stop at lowercase d. Do we have any questions about how the loop is set up on line 34? No questions?
I'm thinking
Yeah.
the conditional statement is what I'm not so sure of. My
Okay.
choice is A
Which
less
line?
than num choices.
Which line?
34.
Line 34. What about
Yeah,
it?
the conditional part.
The condition part.
Yeah.
Okay. What about that?
Are we just converting or just
Let me add parentheses and see if that makes it more clear. Is that better?
I suppose so. Yeah, we're calculating the difference between the difference of my choice in A, and that'll be a letter hopefully not out of bounds of num choice.
Exactly. I'm just checking to see if I am running out of choices. Okay.
Okay.
In other words, if num choices is 4, okay, then lowercase d minus lowercase a would be the last time this condition is going to be true, because lowercase d minus lowercase a in terms of ASCII code will give me a 3. So 3 is still less than 4, which I'm assuming num choices has. So that would be the last iteration, which means as far as the loop is concerned, the loop will go through for the iterations that it's going to go through is star my choice is A, B, C, and D. So there are 4 iterations in that case. Is that making any sense?
Yeah.
Okay. All right. So for each my choice, okay, now I have to see. I have to check to see if it had been used before or not. Okay. So now we need to check whether star my choice had been used in a prior trial or not. Okay, so that means I have to set up another loop to do this. Okay, so the other loop is going to depend on my choice, but this time it's going to go backwards. Okay, because the previous trials have already put their choices into the string, but that is before where my choice is pointing to. So what I need to do in this case is I definitely need a local variable, because I cannot change my choice. My choice needs to stay put to point to exactly where it is pointing to right now. So I would need a temporary variables for this one for sure. So I'm going to say char star choice of previous trials. Okay, and then we'll go ahead and set up another loop for this. Okay, now the thing about this loop is I'm going backwards from 1 byte before where my choice is pointing to, and check each one, okay, to see if it is the same as what my choice is pointing to. If I have a match, I don't have to go any further, okay, because all I need is to say, oops, this one has been used before, I cannot use this one for what my choice is pointing to. So that means I need a condition to remember, can I keep going? Okay, so the usual way that I do this in other languages is to have a boolean, but since C, this is plain C, which does not have the type bool, so I'm just going to use an int here and say not found so far. Okay, not found is good. Okay, because found means I cannot use this particular letter for where my choice is pointing to. So I'm going to initialize not found to be false, which is basically just 0. And then the loop that I will set up here, I'm going to go set up just a typical while loop. Okay, so the first thing I say is while not found, because once it's found, I can exit the loop. Okay, so while not found, and where choice of previous trial is pointing to does not equal to where my choice is pointing to. So the other condition here is choice of previous trial does not equal to well,
I
actually,
think that.
go ahead.
Oh no, go ahead. Finish what you're about to say.
Okay, so I think this is enough because this is just for checking the bound. In other words, if choice of previous trial is pointing to a null character, that means I have already looked at every single previous trial of this entire experiment. Yes, I forgot to initialize choice of previous trial, so let's go ahead and put it here. So we'll go ahead and change this one to my choice -1. Now this is subtracting 1 from the pointer, not what the pointer is pointing to. In other words, I'm backing up the pointer, the new pointer, which is choice of previous trial, to be 1 character before where my choice is pointing to. Okay, so this is the trial that's right before this one. Okay.
Quick question.
Yes, go ahead.
So in this case, you're getting to an open spot, and you're searching to see if the letter that you want to place is already in this sequence of letters, right?
Right.
Can you scroll to your main permutation function where it calls actual recursion? So if I'm not mistaken, the omega in the module it shows because when I did the program the first time, I did that too, to where you actually had to look and see oh, does it fit here, or has it already been used? But when I looked closer at the module, it actually does for each letter is the way the code is broken up, and that way you don't have to look for which is open.
So it depends on how you set up whether you have a set representation or not. So if you already have a set representation and your set representation has an iterator, then you don't have to scan and look for the ones that you can still use. Does that make any sense? But since I'm not using an actual set representation here, so there's no way for me to iterate through all the choices that are still open to me. So what I need to do is to go through every single possible choice and then rule out the ones that have been used before.
Can't you just, in the main code, just so say choices is 3, right? You would just make a string ABC, and then you would just go for each letter and then call the omega stuff.
Yep.
And it would already keep track of, you wouldn't have to search, right?
You still have to search, because if you don't search, then how do you know which one is still available or open to you?
Well, so I actually have it working like that. And I thought, yeah, for sure. And
Okay.
that's based on the module. The module says, this is the part that I was kind of just trying to looking at. So the module says, if you go for each letter, sorry, I'm pulling it up right now.
The module, in the module we can do it that way because we have a subtraction of a set. So we are removing an element from the original set before we do the recursive call.
Yeah, there it is.
Yeah, but I don't have that mechanism here. I'm not using that mechanism here.
Okay, that's what it is. Okay,
right.
Okay, thank you.
All right, so on line 43, the only thing it needs, there are 2 things it needs to do. It needs to decrement choice of previous trial at some point. But the first thing it needs to do is to say, well, what about not found? So not found is going to be not found, and continue, with making sure that it is not found, which means it has to compare whatever choice of previous trial is pointing to, but I want to make sure that it is different from what my choice is pointing to. So this way, I can continue to say, yep, it's still not found, because whatever my choice is pointing to is different from whatever choice of previous trial is pointing to. So this is how I can maintain that true for not found, until um, star my star choice of previous trial does equal to star my choice, then not found is going to be false, which means the while loop is going to exit, indicating that I cannot use it. Okay, and then the other next thing you need to do if not found is continuing to be true. But you can probably do this without worrying of any problem. Is choice of previous trial previous trial is just decrementing by 1, okay? Because we want to keep moving to an earlier trial and keep going until we have either we ran out of stuff or we found one where not found becomes false, okay? So when this loop is done, there are two possibilities that it can exit this loop. One is not found is false. Okay, if not found is false, there's nothing I need to do here because all that means is whatever my choice is pointing to cannot be used because it had been, because I found a previous trial had used that letter already. So if not found continues to be true, then I have something to do. So we'll say if not found, then we can go ahead and do something, which basically means whatever my choice is pointing to is legit. Okay, we can actually use it. But since we already have set it over here, this is where we put in the first one. Um, and this is how we increment it. So we don't have to do any assignment to whatever my choice is pointing to. Instead, we can now go for the recursive call. So we can now call omega, and let me just go back and recall what is the prototype of omega. So num trial has to be decreased by 1 because the next iteration has 1 fewer trials to deal with, and then my choice has to be incremented by 1 because it has to go to the next location in the string because the next trial is going to use the next character in the string, and then num choices remains the same because the number of choices is going to remain the same for all the different trials. Because the way we do the without replacement bit is to scan and make sure that we are not reusing something that had been chosen already by a previous trial. So once again, we have to pass num trials, and that one has to be decreased by 1. And then we can pass my choice, but that one has to be increased by 1. And note that I'm not doing a plus plus my choice. I'm not incrementing the pointer because I need that pointer to stay put. I'm just incrementing it. I'm just adding 1 to it to pass it as an argument, but I'm not changing my choice. And then num choices should remain exactly the same, okay, because we are going to scan through all of the choices in the next invocation as well. So I think this is it. Okay, I think this will do what we wanted to do. So let's go ahead and give it a try. Unless somebody has a question, then I'll go ahead and address the questions first. So between line 34 and line 50 is really the core of the recursive use of this subroutine. So are we good so far or not?
I think it makes sense.
Okay, all right. So the tricky part of this algorithm is, because I was trying to pass as few parameters as possible, so I'm using the string, I'm printing the string backwards. Okay, so I don't have to pass the beginning of the string along with where the current character is supposed to be. So I'm using that trick, to minimize the number of parameters. Okay, so if there are no questions, we'll go ahead and compile the code and see if the compiler has anything to say about that. Oops. And it's always good to use -warn all, okay? So the compiler can perform additional checks, make sure that things are not bad. First argument of int should be an int. of main should be an int. I make it an unsigned. Okay, it's not a big deal, but we'll go ahead and fix it. So even though it's a warning, it's good to get rid of these warnings so that we don't have to think about, okay, this new message, is it a warning or not? Because we just kind of get rid of all the warnings as much as we can. Alright, so we can either use GDB or we can just run the program by itself. And let's just try something relatively simple. The first one is the number of trials. So let's say there are 2 trials and then there are 3 choices for each trial. So this should resemble what the assignment is, what the example in the assignment shows as an example. Let me just kind of pull that up really kind of quickly. I know you guys cannot see it yet. I have to scroll up a little bit. There we go. So in the assignment description, if you pass 2 and 3, it should print out A, B, B, A, A, C, C, A, B, C, and C, B. But in what order is entirely up to you. Okay, it's just that these 6 strings need to be printed. Okay, so now we'll go ahead and run this program and see if it works or not. And it does work, even though the strings are printed out in a kind of strange order. So it prints out BA first, and then CA, and then AB, CB, and then AC, and then BC. That's because things are backwards. I'm printing everything backwards, but it does print exactly the same 6 strings. It's just that the order is kind of not what we expected. So do we have any questions about this program? We can change the program a little bit. We can say, print only have 2 trials but 4 choices. Okay. Now, obviously, this is going to be a little bit longer because it is 4 factorial divided by 2 factorial. 4 factorial is 24, and then 2 factorial is 2, so we should have 12 permutations here. And if you count, there are exactly 12 that got printed. So do we have any questions about this homework assignment? Now, this implementation is kind of minimalistic, because I did not bother to implement the concept of a string, and I certainly did not implement the concept of a Cartesian product, because that would just go ahead and chew up a lot of memory, because it's pre-allocating a lot of stuff. If you use the Cartesian product approach, it's going to store every single permutations, and then you're going to print it out once the entire set of permutations is done. This program just prints out the permutation as it is done, and then it backs up and say, okay, that permutation is done. Let's go ahead and modify the choices for each trial of the experiment, and then print it out again, and so on. So at any time of this particular algorithm, it only maintains 1 permutation. So do we have any questions about this program before we start to look into graph stuff? I'm also looking into the text channel to make sure that I'm not missing anything over there. No questions. Okay, cool. All right. So as I said, there are many ways to implement this program. If you want to use the actual concept of a set and use the actual concept of a Cartesian product, that will work too. It's just that it's going to chew up memory a lot faster than this program. This program only needs to allocate as much RAM as it is needed to maintain 1 string. And we know that the number of trials cannot exceed 26, so that means what I'm actually dynamically allocating is only up to 27 characters, which is not a whole lot. Alright, so if there are no questions, if you guys come up with a question later on, we can go back to this program. But for now, we're going to go take a look at a new topic. Okay, the big omega, big theta, and also big O notation is already done. So if you have any questions about that, this would be a very good time to ask as well. So let me just kind of go back to that module first to kind of remind you guys what we went through the other day. So this is the module that we talked about on last Wednesday. And the conclusion is really type bound. Okay, type bound is what we really want. Okay, type bound is represented by big theta as a notation. So if f of n is an element of big theta of g of n, that means, okay, if and only if g of n is both the upper bound, okay, big O is the upper bound, and g of n is also the lower bound because big omega is representing lower bound. So in the case of g of n being both the upper bound and the lower bound of an actual time complexity function f of n, then we call g of n the type bound of f of n, which is kind of what we really want, because it's not too difficult to have an upper bound, especially when you can say, well, we can have a way overestimating upper bound. Okay, that's fine. It's pretty easy to come up with. And it's also not difficult to come up with a lower bound, okay, because a lower bound only has to be smaller than what f of n really is. And you can always say constant time, right? Constant time is the lower bound of everything. But is it really useful? Nope, it doesn't give you a whole lot of information, doesn't help you deciding which algorithm to use, and the trade-off between algorithms. But a type bound gives you the best information, the most information that you need in order to make a decision of which algorithm should I use. So are there any questions, about this topic? Okay, because basically we went through a lot of definitions like supremum, infimum. We talk about limit superior, limit inferior, blah blah blah, all the way just to get to exactly what does type bound mean. So that is what we talked about on last Wednesday. So do we have any questions about this? We don't have any questions. Okay. So the application of what we learned in this particular module, even though we introduce a lot of terms and they don't seem to be very important, the application of this module is how do you choose? Okay, so we're going to go to sorting algorithms in Wikipedia. Okay, so there we go. So there are many sorting algorithms. For those of you who like to watch videos to learn something, you can look up Hungarian dance sorting algorithms. Okay, go to YouTube and look for those. And they have Hungarian dance to illustrate bubble sort, insertion sort, and so on and so forth. So it's really quite entertaining. Okay, but for the focus of what we are doing here, we are looking at efficient sorts. Okay, so if I skip the topic, yes, Iraj likes those videos. I think he is the one who mentioned that to me. Okay. So when we look at efficient sorts, okay, you can see that merge sort has a worst case running time of big O of n log n. So once again, this big O really is not what big O is, not how big O should be used. Okay, this is the best way to put it, because big O of n log n also means big O of n squared, which also means big O of n cubed, because all of those are faster growing than n log n. Okay, so this is really, this really should be replaced by a type bound, which is big theta notation. Okay, so we always want to look at the worst case scenario because there's no need to look at the best case scenario. It just doesn't make sense. Okay. So merge sort is not really well understood. This easily applies to list and not only arrays, because it only requires sequential access and not random access. This is one thing that a lot of people do not know about merge sort, because most merge sort algorithms use an array implementation. So people think that merge sort will only work if you have all the data in arrays. That is actually not the case. Okay, the idea of merge sort, or the way it came about, was to sort items that are stored on computer tapes. Yes, I did say computer tapes. Okay, we're talking about mainframe computers with reels of tape turning. Okay, back in the good old days. Okay, so the idea of merge sort is if you have one big tape that you want to sort, you will need two tapes on two additional tapes for sorting. Okay, because you need to split first, and then once you split, all the data from the original input tape would now be stored on two different tapes, and then the merge is going to run those two additional reels of tape as input, and then the data stored on those two reels of tape will now be merged back onto the one single reel of tape to begin with. So basically, you're just moving from 1 to 2, 2 back to 1, 1 to 2, 2 back to 1, and you would do that up to log n times, n being the number of records. So this is exceedingly fast, okay? Because tapes, as much as they seem really archaic and whatnot, they were actually very fast compared to hard drives at the time. Tapes are actually, they have a higher throughput. In other words, the number of bits that can be read is actually pretty high with tapes, and it's also a very compact way to store data. But these days, since we have SSDs and whatnot, it doesn't seem that it's useful anymore. Merge sort doesn't seem like it's useful anymore. But I would even argue that even by today's standard, merge sort still makes a lot of sense. Okay. And I'll just kind of briefly explain this part, just so that you guys have a kind of perspective of why old technology or algorithms that were derived for old technology still has a place today. So let me just ask you one thing, okay? If you are writing a modern app in the cloud and you are trying to pull data from another server, okay, that is sitting somewhere else in the cloud or in the internet, how do you get data, massive amount of data, from one server on the internet to another server on the internet? So I'm reading the text here, and if you guys want to just, yeah, go ahead.
There's a website that I used when I was working for Berkeley. It can transfer like 300 gigabytes.
Hmm.
Forgot.
But how does it do it? How does it get it done?
SSH.
SSH. Okay, very good. Okay, so SSH, like many other protocols, is based on TCP/IP. Okay, I don't want to turn this class CISP 440 into a TCP/IP class, but we'll just go ahead and say, TCP/IP is just an abstraction of a stream. Okay, so all of you should know what a stream is, because that concept should have been introduced in maybe a little bit in CISP 360, but by the time you get to 430, you should know what a stream is, right? Is that okay?
Yeah.
Yes? Okay. So what is a stream very, very good at? Sequential access, right? Get me the next character, get me the next character, get me the next character. That is what a stream is very, very good at. Now you can say, but I can seek too, okay? I can skip items, I can seek back and forth, and so on and so forth. Well, that's not really what a stream is very good at, even though it can do it, but it's not what is very efficient at. What a stream is extremely efficient at is sequential access, okay? I just want to read the next character for an input stream. I want to read the next one, the next one, the next block, okay? When you want to write to an output stream, I just want to write the next character, the next character, and the next character. So, hey, wait, hold on a second here. Are you telling me that streams actually have very similar properties compared to the physical properties of tapes? The answer is yes. Okay, so this means if you want to perform very efficient sort, and you have a very efficient way to write to streams and also read from streams, merge sort works really well without using a lot of RAM, because merge sort only needs to maintain 2 records at a time in order to get its sorting done. So that means merge sort is also well suited in today's cloud age, okay, age of the cloud, because if you can open streams, input streams, and output streams, and use streams in a very, very efficient way, which means TCP/IP and internet connections that are up to like 10 gigabits per second. Okay, if you can do that, that means you can also use merge sort to sort a huge amount of records in a very short amount of time, and it does not need any RAM. Okay, that's the best part of it. It doesn't need a whole lot of RAM to get it done. Okay, so what I want to point to, getting back to what I wanted to point out to begin with is these are all sorting algorithms. So when you look at the best or the average time of the time complexity, they all have n log n as the big theta. Um, Quicksort is an interesting one because Quicksort actually has a worst case of big O of n squared or big theta of n squared in the worst case. But depending on how you choose the pivot for Quicksort, people can argue and say that its average case or its worst case can also be seen as big O of n log n. Um, but this is what we need to pay attention to is if you choose the wrong sorting algorithm, so instead of using a n log n sorting algorithm, and you use a n squared, type of algorithm, for a small test case, it will work just the same. Okay, the difference is not really obvious until n gets large, and it makes a difference. Okay, because when you have to deal with a small problem, your test cases are small, nothing seems to be wrong. But as your test cases get larger and larger, and when you deploy your application, that's when things will start to go really bad because the time complexity is growing a whole lot faster in the case of bubble sort compared to, say, merge sort. Okay, so that's basically how you apply these concepts when you go to work. Okay, now when you go to a 4-year university, there will be a class called the analysis of algorithms. So those classes will basically talk about things that are a little bit more abstract than things that we talked about in this class. In other words, they will ask, can we find a sorting algorithm that is faster than n log n? Okay? In other words, we are not even looking at a particular algorithm. We are talking about every single possible sorting algorithm. What is the best time complexity that you can have with every single sorting algorithm, theoretical or otherwise? And the answer is actually n log n. This is the best we can do. But how do we prove that? Okay, that is up to the class that you'll be taking as an upper division class, typically called the analysis of algorithms. So if you like this class, you'll like that class too. All right, so I think we are done with time complexity. So the notation of big O, big omega, big theta is now done, and we are moving on to graph stuff. Okay, so graph stuff is kind of important because when you look at, say, Google Maps, okay, and you ask, how do I go from where I am to this destination as quickly as I can? Okay, now I'm pretty sure Google uses an algorithm that may be based on the algorithms that we'll be talking about, but modified. Okay, it's not going to be exactly the same, but you can see how being able to find the shortest path between 2 points is a pretty common problem, optimization type of problem in computer science. Okay, so we'll go ahead and basically start at least introducing an algorithm that can help us solve this kind of problem. And we'll also go through some terminology first before we get to the algorithms. So we're going to start with section 2. Section 2 basically just talk about what is a graph. So a graph typically is represented by two things. It is represented by, there's a set of vertices and also a set of edges. Okay, so V is the set of vertices and E is the set of edges. There's really not a whole lot of restriction of what a vertex can be in V. But typically in our class, we just use a lowercase letter to represent a single vertex. But there's no requirement that a vertex has to be a lowercase character. Okay, it can be by itself a set too. Okay, it can be anything. It can be a number. It can be a GPS location. It can be a lot of different things. Okay, now, but once you know what the vertices are, then edges, okay, is a subset of the Cartesian product of V and V. Okay, so are there any questions about these notations? Because we are basically reusing the same set notations from really early on in the class. So everything in E is a 2 tuple where the first item and the second item have to be vertices from the set of V. Okay, so that's basically the restriction of what you can have in the set of edges. In this class, we are only working with directed graph. A directed graph means each edge is directional. So it is, if the edge is represented as AB, that means it's going from vertex A to vertex B. It is representing that there is a direct edge leading from vertex A to vertex B. Okay. On the other hand, if we have a graph that is undirected, all that means is AB in E also implies if and only if BA is also in E. So with an undirected graph, so the bottom line is an undirected graph can be represented as a directed graph. It's just that you have twice the number of edges, because for each way you can go from A to B directly, there's a B to A edge as well. But it can be represented basically using the same mechanism. So are we okay so far with the concept or the terminology of what is in a graph? I can show a few examples. Okay, so let me just go ahead and use mousepad to show some examples. And by the way, I found a really kind of interesting editor. It's called Notepad Qq. Notepad Qq is implemented mostly, if not entirely, in Node.js, in JavaScript. So its extensions can also be written in JavaScript, which gives you a lot of opportunities to add your own functions and your own features into this particular Notepad. I think it's called Notepad QQ because it is kind of a play of the name of Notepad++. Um, but it's really kind of interesting. You can do your own syntax highlighting. You can implement your own logic for just about anything you want. It's highly extendable because of that. But for this, demonstration, I'm just going to use mousepad. All right, so let's take a look at a graph that is represented using the set notations. Okay, so here's G, which is a graph, and we're going to use V and E to represent this graph. So let's just say that in this case, V has 4 vertices. Okay, so we have A, B, C, D as our vertices, and then in E, we are representing our edges. So let's just say that there's an edge going from A to B, there's an edge going from A to C, there's an edge going from B to C, there's an edge going from B to D, and there's another edge going from C to D. So when you look at it this way, it's kind of difficult to visualize. So the best way you can do, when you try to understand a graph concept, is to draw a picture. Okay, so when you draw this picture, okay, we can start with A to B. Okay, so you can just kind of approximate an arrow like this. So A is called the tail of an edge, and B is called the edge of an edge. Okay, so if you have AB stored as a 2-tuple in the set of edges, vertex A is known as the tail, and vertex B is known as the head. Does that make sense to you? Okay, no one is commenting. No, it does not seem to make a lot of sense. Okay, it doesn't make sense until you look at this as an arrow, as in an arrow that you shoot from a bow. Okay, so B is represented as, is called the head because it is the head of the arrow. A is called the tail because it is the tail of an arrow. So that is why these two vertices got its name, when it is referred to as components of an edge. Okay, so is that okay? Any questions? Nope. Okay. All right, so A is also going to C. Okay, so I'm going to use a vertical bar. So I'm just approximating an arrow over here, and we'll use uppercase V, as an arrow pointing down. So here is vertex C. So A is going to B, A is also going to C. We have vertex B going to vertex C. So that gets a little bit harder to represent. I'm going to have to use some slashes here. But you get the idea, I'm hoping. Okay, we just kind of have to approximate this a little bit. Uh-oh, it doesn't quite work out entirely this way, but we can we can do something like this. Okay, it looks close. Okay, so A goes to C, A goes to B, and then B goes to C, and then both B and C would go to D. Okay, so if I want to extend this graph a little bit, I'm pretty sure most of you do not want to see me wasting my time to approximate a graph using characters. Okay, so I'm just gonna make this a little bit shorter now. Okay. Okay, here's a plus, and then we just have a whole bunch of vertical bars. Ah, nope. There we go. I'm pretty sure most of you get the idea, but I just want to finish this so that it is complete as an example. There we go. Oops. Dash dash plus. There we go. So you can use a kind of more graphical representation that makes it easier to understand. Just be aware that sometimes the graphical representation it's good when the graph is simple, but when the graph has a lot of edges, looking at the graphical representation can actually be more confusing. Okay, so this is really just for us to start to understand what a graph is, but when it gets down to it, it's better to look at it from the more abstract perspective. Okay. All right, so terms, originally I introduced a lot of terms that relate to describing different things in a graph, but I condensed everything here because I just want to get to the algorithms as soon as possible. Okay, so I'm only explaining what a path is in a graph. Okay, so this is a notation that basically says P is a path. So when we look at a path, the first thing we notice about a path is it is a tuple of vertices. In other words, it is quote unquote a list of vertices where the ordering is important. Okay? So edges from E must lead from vertex to the next on a path. Okay? So this is basically how I express that. For every I as a natural number, if I is less than bar P bar minus 1, so bar P bar is basically just looking at the length of the tuple. Okay, so I is a potential index. And what it says here is P of I plus 1 as an edge has to be in E. And I think it's off by 1 because, if I can be bar P bar minus 1, then I plus 1 can potentially be bar P bar, which is out of bound when it comes to that particular tuple. So let me fix that on the side first because I really don't want to keep incorrect notes around. So I'm just working off the screen right now to fix that error. And this is 0310. Alright, so we are changing the range of I. It has to be, oh, okay, it's actually correct. Okay, I correct myself because I has to be less than bar P bar minus 1, which means I can only be as large as bar P bar minus 2. Then it makes sense because when this I here equals to bar P bar minus 2, then I plus 1 is bar P bar minus 1, which is representing the last vertex of the tuple representing a path. Okay? Alright, so that's the concept of what a path is. Oh, the other thing about a path is a path cannot contain duplicates of a vertex. Now, this has nothing to do with the concept of a tuple. It has to do with the concept of a path. So a path cannot get back to the same vertex. No vertex can appear more than once along a path. And then between any two vertices along a path, an edge has to exist. So that is basically the bottom line of what a path is. So when we look at the example that we just presented a little bit earlier, so one way to define a path is A B, C, D is a path. So when we look at P, okay, so we can say P is a path which is just A, B, C, D. Now, how do we know this is a path? First of all, is any vertex appearing more than once in the tuple? The answer is no. Okay, A, B, C, D, each one only appears up to once in the path. So that's good. The second question is there an edge between every neighboring vertex within the tuple? So between A and B, do we have an edge? Okay, we just look up the set of edges and we say yes, there is one. Between B and C, do we have an edge? The answer is yes, we have an edge over here. Between C and D, do we have an edge? And the answer is yes, we also have an edge between C and D. So now this particular tuple, ABCD, is meeting all the requirements, so it is considered a path. Let me consider another path or potential thing that may or may not be a path. Okay, so let's just look at ABD. Okay, is that a path? Is any vertex in this tuple appearing more than once? The answer is no. Okay, A only once, B only once, D only once. C does not appear anywhere within this tuple, which is fine. Okay, next question. Do we have an edge between every neighboring vertex within this tuple? Is there an edge between A and B? Yep, there's one. Is there an edge between B and D? There's one as well. Okay, right here. So ABD is also a path. What about AB and then BD? Okay, this is not a path. Okay, well, it's not a path, just visually, because we can see that B is appearing twice. Okay, so that automatically disqualifies this particular tuple as a path because at least one vertex along this path is appearing more than once in the tuple, so it is not a path. Okay. The other reason why this is not a path is because when you look at the two neighboring vertices, B and B, there's no edge. Okay, B does not have an edge back to itself. It doesn't mean that that cannot happen. Okay, now in certain graphs, it is okay for a vertex to have an edge going back to itself. That's perfectly okay. But in this particular graph, there is no such edge going from B ending up with B. So for those two reasons, okay, each one is already enough to disqualify this tuple as a path, but this is definitely not a path. So are we doing okay so far in terms of understanding what a path is?
I
Okay,
believe so, yes.
go ahead. Is it good? Okay. So there's only one more concept before we can look into the algorithm. So we have a function called distance. So the distance function is mapping edge to to real numbers. The asterisk here means it is non-negative. So it can be 0. Okay. So the distance of an edge can be 0, but it cannot be negative. Okay. It can be a real number, any real number other than a negative number. So basically, we start to associate, numbers or real numbers with edges. So in this case, if I want to represent, distance as a function, so we basically have to say AB is an edge, and we have to now associate it with a real number that is non-negative. So let's say it has a distance of 2. We look at the edge AC, and then we have to now associate a real number. So it can be a fraction number. Okay, it can be 0.33. Okay, that's perfectly okay. We look at the edge BC. It can be 0. Okay, the distance between the distance of an edge can be 0. Okay, if it is appropriate, in that case. And then BD can have a large number, let's say 100, 1,000. Okay, doesn't really matter. It's just an example. And then CD as an edge, may have a distance of 10. Okay, so this is one way to represent a function D that is mapping edges to their distances. So do we have any questions about the concept of distance function that maps edges to non-negative real numbers? All right. So we got all the basic terms ready. Okay. So it's now time to talk about the algorithm. which is going to be the confusing part. Okay, so by the time we are done with describing, let's say, Dijkstra's algorithm, just because it is the first one on the list, it may be a good idea for you guys to apply Dijkstra's algorithm on the graph that we have just constructed over here, okay, as an example. Okay, so what we'll do is we're going to analyze the algorithm first, or at least describe the algorithm, and then we'll go ahead, if we have time, to get started and maybe go through a few steps of the algorithm. Okay, so I'm just going to talk about each step of the algorithm step by step. Okay, this is the first step. The first step is not even doing anything. All it is doing is to explain, what symbol is representing what in this particular algorithm. So we are using uppercase G to represent the graph itself, which has two components. V is the set of all the vertices, and E is the set of all the edges. And then D is the function that maps all the edges to their distances. Okay, which is basically the same as the notation that we have already talked about. So there's nothing new on the first line. The second line is let S as a subset of V to be a subset of vertices identified as destinations. And you're correct, okay? I did not make a mistake. These are destinations, these are not starting points, okay? So the Dijkstra's algorithm that I present here is a little bit different from Dijkstra's algorithm that Iraj presents in CISP 430. The one that he presents can only find the shortest path to one single destination, whereas this particular algorithm will find shortest paths from every vertex to at least one of the destinations. Okay, so let me say that one more time, okay, because this is a little bit tricky. This particular algorithm will find the shortest path from every vertex to a destination. All destinations are considered equal, so getting to any one of those destinations is considered having the problem done, and they're all done, quote unquote, equally good. Okay, so to understand why this is actually applicable or why this is useful, think of yourself in this scenario. Okay, you're taking a young child with you to Six Flags. Okay, and the young child says, I need to go to the bathroom. So now your destinations are every single bathroom that is suitable for the gender of the young child. Those are your destinations. Okay? So that's why this algorithm is useful, because once you apply Dijkstra's algorithm to the map of Six Flags, and as soon as you know which vertex you're on at this point, you already have the shortest path to a bathroom. It doesn't matter which bathroom, because every bathroom is equally good. Okay, at least that's the assumption. So is that okay? Does everybody understand why it is useful to have an algorithm that can find the shortest path between every vertex and a destination? And we can have potentially a set of destinations, so there can be more than one destinations if we want it to be. Do we have any questions about this particular property that we are assuming in this algorithm? Cool. All right. So if you're transitioning, or if you already understand Dijkstra's algorithm from CISP 430, you probably want to make a mental adjustment to make sure that you understand this algorithm as Dijkstra's algorithm for 440, because when we get to the exam, okay, if there's an exam question on Dijkstra's algorithm, I'm going to use this algorithm as the grading standard. So the behavior of what you're doing, of what you're tracing, needs to match this algorithm and not the other one that Iraj talks about in his class. Okay, so the next line here says for each v in uppercase S, so for each destination vertex, we assign a 0 to L of v. Okay, so now we are starting to introduce a function, and we are basically constructing a function as we go. L of v is 0, because what L of v is indicating is the length of vertex v to a destination. Okay, so let me repeat that. L of v is the length of a path known at this point. Okay, let me back up again. Okay, let me say that one more time. L of v is the length, and therefore the L, of the shortest path that is known at this point between vertex v and a destination. Whew, okay, is that good or not? Okay, because if you have a question about what I just said, now would be a good time to kind of pause or ask about it. Okay, no questions? Very good. All right, so next line is look at all the vertices that are not destinations. Okay, so when we look at the set v minus s, that would be the set of all the vertices that are not destinations. So if v is not a destination, then we change the function L, so the L of v is infinity. Now, I understand that infinity is not an actual number, but we are basically just saying that we do not know whether there is a way to go from vertex v to a destination or not. That is what this assignment statement is about. It's basically saying, let's just assume there is no way to go from vertex v to one of the destinations, because this is before we even explore the map. So we're basically just making an assumption that, okay, let's just assume there is no way to reach a destination from vertex v. Okay, so are we good so far with the first 4 lines of the algorithm? Okay, no questions. Then we move on and initialize a new variable. So Q is a set because it is getting the value of uppercase S. So we are initializing what we call a boundary set. So Q is a boundary set that is initialized to the set of all the destination vertices. So basically, instead of starting with a single start vertex, we're starting with all the destination vertices. Okay, and then E prime is an empty set. This is a set of solution edges. In other words, the edges that are actually on shortest paths from any vertex to a destination is going to be in E prime. But since we are initializing for the algorithm to run, E prime is an empty set to begin with, because hey, we don't really know how to get to a destination except for destinations themselves. Okay, so that's why E prime is initialized as an empty set. All right, so do we have any questions about the initializations as well as the variables or symbols that we have used up to this point? All right, can I explain that again? Okay, so Q gets S is basically saying Q as a set is initialized to what S is. So Q is a variable that will change, when we get to the actual logic of the algorithm. But the set S is a constant because it is really just the set of all the destinations, which does not change over time. Is that okay? Okay, cool. Okay, so right, the next line, it says as long as Q is not empty, we got stuff to do. Okay, so the first thing we do in inside the loop is we select a vertex in Q. Q is a set of vertices, so we're going to select one vertex out of Q, but we are not just going to randomly pick one. Okay, we're going to pick a V such that this thing is true over here. Okay, so what do you think this is saying? Okay, V is what we want to choose from Q, and W is only needed to describe the property of V, which we are picking from Q. Okay, so you can read the rest of the description. I mean, that basically tells you what is the special property of V. V amongst all the vertices has the shortest length to a destination of all the boundary vertices. That is what we are choosing. So in other words, Dijkstra's algorithm is a greedy algorithm. Okay, it just says out of all the options, okay, let's just pick the one that has the shortest length of that has a the shortest length known to the. Okay, let me rephrase that. Where the length of the shortest path to a destination is the shortest. Okay, that's the best way to describe it. Okay, so it will pick that first. In other words, it's basically asking which one of these vertices looks the most promising. That's what it's choosing. And then on the next line, we are subtracting the set of just V from Q. In other words, we're removing that vertex from Q because we are now considering we're expanding that certain boundary vertex at this point. And then this is a nested loop. The nested loop is basically saying, let's look at all the edges that fits this requirement. So the requirement that we are looking at here, this V and this V and this V here are the same. Okay, so we have already chosen what V is supposed to be, but this W is really just saying, well, we are only considering edges that end up at V. Okay, we are looking at incoming edges of V. So when we look at this particular set notation here, this is the set of all the incoming edges into vertex V. Or the other way to put it is all the edges in this particular set has V as the head of the edge of the arrow. Do we have any questions about this notation? No questions? Okay. So we are looking at all the incoming edges to vertex V. Okay, so Bo has a question. I'm going to wait a little bit here. Okay, with E as head, no, E is not the head, V is the head. Vertex V is the head of all the edges that we contain within the set that is highlighted on the for each line. Okay, that's fine, no problem. And then we just call that edge E. You know, it's just easier to refer to the edge as E because otherwise we're gonna have a lot of notations here that needs to expand to the tuple WV. So we just look at WV as a single edge E. Then we ask a question. Okay, this is the question that we're asking. But what we really want to focus on is why do we ask this question, or what the question is really asking. So this really kind of have to go back to the definition of L. You know, what is L of V or L of W? What is the meaning of that? Okay, so L of V, once again, is the length of the known shortest path from V to a destination vertex. L of W is kind of similar, right? It is L of W is really the length of the known shortest path from W to a destination. So now what we are asking is, we know there's an edge going from W to V. Okay, so we are now asking if we consider the distance of the edge going from W to V, and we consider the length of the shortest path from V to a destination, and then we compare that sum to the length of the shortest path from W directly to a destination. If the left hand side, if this expression is less than L of W, what does it mean? Okay, so let's not look at the rest of the code for this time. We just want to know, what does it mean if this less than is true? Okay, what does it mean?
At the length of V or the length of V W.
I think it just means that we just found a shorter path from W to a destination. Don't you agree?
Yeah.
Cool. Okay, so if we just found a shorter path from W going through V to a destination, that is the shorter option compared to what we have found so far, then we have to remember it. Okay, because we have to make some adjustments because we're excited. This is cool. We just found a better way to go from vertex W through vertex V to a destination. That proved to be a shorter path compared to the path that I have already found from W to a destination. That is what this condition means. Is if it is true, that means we just found a shorter path from W to a destination. So the first thing we do is to update it. It's like, woohoo, we just found a shorter path, and this is the length of the shorter path. Okay, so that's the first thing we do. And then the second thing looks really confusing, but that's all this is doing is to say, let's undo, okay, all the edges that we have put into E prime that correspond to the not shortest path from W to a destination. That's what this highlighted part is doing, is just to say let's undo that, okay? Because what we found before, which is W going through another vertex V, which is already in E prime, that is not an edge of the shortest path anymore. Let's go ahead and get rid of it. Okay, that's what this particular for each is doing. And then we have this line here, which is basically saying let's put the right edge into E prime, because we already know that WV, okay, is the edge that can lead from W to the destination along the new shortest path. So let's put that into E prime, because after all, the purpose of E prime is to remember the edges of shortest paths. Okay, so that's why we're adding the edge WV to E prime. And then the very last thing we do inside the conditional statement here is to say, oh, but that means W has just gotten its L value changed. So anything that goes to W, okay, may have found a shorter path as well, because now they might want to go through W to a destination instead of the path that is leading from those vertices to a destination. So that's why we're adding, or we are putting a union into Q, so that W is now in Q, so that at some point we're going to pick W from Q and say, okay, there's a potentially shorter path for you, because we just found a shorter path from W to a destination. So anything that is going to W may now have a shorter path, and so we need to make adjustments because of that reason. So that is the reason why we are having a union to put the singleton set with W into Q. Okay, so this is the loop here. So basically for each iteration, we pick out one thing that just got its L value being getting smaller from Q, and then we ask, okay, who can go to U, because all of those other vertices may have just found a shorter path to a destination. So we look at every single one of those vertices that is going to V, and we ask, did you find a shorter path? Did you find a shorter path? Did you find a shorter path? And did you find a shorter path? If the answer is no, okay, the new path is not shorter, we go like, okay, fine, keep your current shortest path. It's no big deal. On the other hand, if we just found a shorter path from W through V to a destination, then we have to put W itself into Q, because anything that is going to W may now have a shorter path to a destination. So that's basically the core of the logic of Dijkstra's algorithm. Okay, the last line here, which is defining a solution graph, is trivial, okay, because G prime is really just a very similar graph compared to the problem graph itself. The only difference is, okay, instead of using E, it is using E prime. It still has the same vertices, but it's not using the original V, E. It's using E prime, which only consists of edges that we know should be along a shortest path. So I think we are running out of time today, but one thing you can do with Dijkstra's algorithm is to run it against the graph that we have already talked about here. Okay, this should be a really easy graph to find your shortest paths. So the idea is not to use this as a mechanism to find the shortest path, but to use this as a mechanism to test to see if you can follow Dijkstra's algorithm. And to use Dijkstra's algorithm, I need to give you one extra piece of information, which is D, vertex D is the only destination in this problem. Okay, you can always adjust it. Okay, if you say, but I want vertex B and vertex D to be both destinations, well, so be it. Okay, that's fine too. Okay, or if you want to make it kind of really trippy and go like, let's pick vertex C as a destination, because if I pick vertex C as a destination, then there's no way for vertex D to reach a destination because there's no edges connecting from D back to C. There are no paths to go from D to C. What's going to happen with Dijkstra's algorithm in that case? Well, if you want to do it that way, okay, that's fine. Okay, change the set as to only have vertex C. Then you will find out, how do we represent that a vertex has no path whatsoever to any one of the destinations. So all of these things are the things that you can do before Wednesday to help you understand Dijkstra's algorithm. And or if you say, I tried this but I cannot follow the logic in section 4, you can ask those questions on Wednesday as well. Is, okay, I'm not really quite sure what this line means. Okay, what do we do with that line? So on Wednesday, what I'll do is I'm just gonna go through this exercise, okay, with this particular graph, or I may give myself even a more complex graph to follow because this one is really easy. It doesn't demonstrate some of the things that Dijkstra's algorithm can do. So that's what we'll do on Wednesday, is to kind of go through Dijkstra's algorithms line by line, step by step by hand. And if we have time left on Wednesday, then we'll start to get into A star algorithm. Okay, and then we'll start to notice differences between the two. Why is this one better in what way, and why is the other one better and in what way? So that's what we'll do on Wednesday. All right. So do we have any other questions? Nope. Okay, I can see people are signing off. All right, cool. So I'm gonna stop the streaming, starting with YouTube. And if you do have any questions, go ahead and